All right. Today our focus is going to be on the curved surface area, and I'm going to narrow it down to cylinders and cone. So the shape on the left is a cylinder, and the shape on the right is a cone. Just in case you have problem identifying which is which. Now we already know the. I'm assuming rather that we know the various parts of a cylinder and a cone. They are three-dimensional shapes, right? Because they have height. The cone has a radius, circular base, and obviously a radius. The same thing with a cone. Now, what's the curved surface area, you may want to ask? What do you mean by curved surface area? Now, when you have a shape, you may be asked to calculate the surface area. Just like, let's say you have a cube. A cube has 8 faces, and each of those faces have area. So you might be asked to calculate the surface area. That means you add all the areas of the shapes of the faces rather. So but when you ask to calculate curved surface area, that means the shape must be curved. Just like a cylinder can be curved, a cone can be curved. So the curved surface area of this cylinder is actually this curved part, and that of the cone is this curved part. So that's what we mean by curved surface area. You might be asked to calculate that. Now, let me just keep this video very simple and short. Now, you see the shapes that I have drawn below each of the shapes that we want to find the curved surface area, which is the cylinder and the cone. These are the shapes that actually form them. Are we together? Let's start with the cylinder. We'll do that of the cylinder, we go to the cone. Now, I believe maybe you have one time in your life, maybe you bought a cardboard, bought paper, and then you roll it into a cylinder. So you see that you've actually used a rectangular cardboard to form a cylinder. All right. So you can imagine when we have this cylinder now, you can imagine if I take a scissors and I run through the cylinder, cutting it, from this line that I have drawn now, is going to open up the cylinder, forming back this rectangle, right? Therefore, if we can find the area of this rectangle, it will be the same thing, that it will be equal to the curved surface area of this cylinder, because the areas must be the same since it's this rectangle that formed this cylinder. So that's how I'm going to do it very easy. Now the problem becomes, what is the length and breadth of this rectangle relative to the cylinder? So one thing we can clearly see is that this height is always going to be the breadth of the rectangle. So I can call this height h and call this h. All right. Now this length, how will I derive it from the cylinder? Now one thing I want you to picture with me is, imagine you have a circle, because you can clearly see that the base of the cylinder is a circle. Imagine I have a circle and I do the same thing and I cut this circle. All right, so that I cannot stretch or extend the circle as a rope, something like that, as a straight line. What will be the length of that line? Of course, you know that the length is going to be equal to the circumference of this circle, which is 2 pi r. That's how we calculate circumference. I assume you already know that for this video. So we're going to apply the same principle. When we cut the cylinder, that circular base is going to open up to be circumference. That is going to be the length of this rectangle, so which is 2 pi r, and the r is going to be equal to the radius of this cylinder. That's the radius of the circular base. So all we need to do is just to solve the area of this rectangle, and we know that the area of rectangle is length times breadth. So that the area of this rectangle, which is, so I'm going to just say, instead of calling it area of rectangle, I'm going to call it the curved surface area of the cylinder, is the length, which is 2 pi r, times the breadth, which is h. So anytime you're asked to calculate the curved surface area of a cylinder, you use the formula 2 pi r h, where h is the height of the cylinder and r is the radius of the circular base. Now that's a very good one we've done there. Now, the next thing we're going to talk about is that of a cone. Now, a cone is formed by a sector. Now, if you want to understand this part of the cone, I will need you to watch my previous video where I showed the relationship between a cone and a sector, because I'm going to draw something from there. Let me just write it out right away. A relationship we establish is that the angle formed by the sector, when I mean by angle, this sector of a circle, because it's a part of the circle, so it's going to be an angle that is a part of the total angle in a circle, which is 360. So that this angle is equal to the radius of the cone, which is small r, divided by the radius of the circle, which is that of the sector as well, all right, times 360 degrees. This was a relationship we established, right? So I established this relationship perfectly. So if you don't understand and you have a passion to learn, thoroughly, and not just cram things up and down, you can go back and watch that video. So now, using this relationship, I can now build my point. Now, when you fold, it's just like the same game we played on the left-hand side. If you fold this sector down, you are going to get a cone. It therefore means that the surface the curved surface area of this cone is going to be equal to the area of this sector, because it's this same sector that was folded into that cone. So we can play the same game. We can say that now the question now is, what's the formula to calculate the area of a sector? We know that the area of the sector, I'm going to call it, let me do it somewhere here, a sub s is equal to theta over 360 degrees times pi r squared. I'm using capital R because it's going to be the radius of the circle from whence the sector was formed. So the capital R, which you can see on the sector. Now, we're saying that this area of sector is also equal. Okay, I'll use another color there, blue. This is also equal to the curved surface area of the cone. I hope this is not jam-packed. So now we just go down and establish our point, so we'll be out of your way. Now, look how I'm going to do. I'm going to use that relationship. Therefore, instead of using theta, remember we have already established that this theta is equal to r over r times 360. Go back and watch the video if you don't know already. Now you may ask, why am I replacing the value of theta with that? It's because of I want to get the curved surface area of the cone, with respect to the values that are obtainable in the cone. Not, having theta, because this cone there is no angle. Because this theta we're talking about is the angle of sector, not angle of cone. So I want to do everything in the formula relative to the things that are obtainable in the cone. Just like in our first one we have done for cylinder, we have 2 pi RH. This 2 pi RH, the H is the height of the cylinder and the R is the circular base of the cylinder. Meaning that everything we need to solve this is going to be provided for us in the cylinder. So that's the same thing we want to do. So without further ado, I'm going to replace theta with R over capital R, times 360 degrees. Now over 360 degrees. So everything I've done here, everything I've written here for this is just the same value for theta. So I just changed theta with what is equal to, and then times, I can now say times pi r squared. Good. Now, what you can see clearly from here is that 360 is going to cancel 360 there, and this r will cancel this r, or rather, let me just cancel the square. This r is going to cancel one r here because there are two here, leaving only one. So what are we left with? We're left with, remember, we're calculating curved surface area, so I can now write boldly, the curved surface area of a cone is r times pi times another r. Simple. So finally we can now say that the curved surface area is equal to, now I want you to look at something. Please, another relationship we established in the last video is that the slant height, look at what I've called it, L. The slant height of this cone is the same exactly as the radius of the sector that formed the cone. Now you can clearly see that if you fold this sector to form the cone, the radius of the sector will also be equal to the slant height of the cone. Therefore, it is good for me to replace, since I want to do everything in terms of the cone and not the sector. The radius is from the sector. I want everything from the cone. So I can now say this is r times pi times L, since L and R are the same. Finally, men and brethren, the curved surface area of the cone can now be written as pi. I'm just taking pi first. It doesn't matter. Multiplication is commutative, right? But just to do it the way you likely see it in your textbook, pi r and then L.